Hello, everyone. Welcome to Science Café. Science Café is an event that's been sponsored by the Faculty of Science for a number of years. I estimate about 13, at least since 2008. And today I'm pleased to have Dr. Jason Crann from the School of Mathematics and Statistics. Dr. Crann obtained his PhD from Carleton a number of years ago. He's a specialist in operator algebras and quantum groups, spent a few years in France, and he mentors regularly undergraduates and graduate students and gives talks to undergraduates as well. So I'm pleased to have Dr. Crann here with us today to speak about quantum entanglement. Okay, Jason, the floor is yours.
Thank you, Angelo. So let me just pull up my slides here. I assume that's okay. Angelo, you can see this, I assume?
Yep.
All right.
All good.
Okay, so thank you everyone for coming today. It's a real pleasure for me to speak on a topic that I find quite fascinating from both a mathematical and a physical perspective. So I'm going to start by just saying a few words about myself. And then I'm going to spend quite a bit of time attempting to provide a picture, which I find very helpful when thinking about the fundamental unit of quantum information, which is a quantum bit, or qubit for short. And then I'm going to, through that picture, I'm going to define entanglement in the context of two qubits and discuss some of its fundamental and paradoxical features. Okay, using an example that really originated in seminal work of Einstein, Podolsky, and Rosen, which is this EPR abbreviation here. And then I'm going to mention some applications to quantum information, in particular this fascinating quantum teleportation protocol. And then I'm going to finish with some current research directions, which I find interesting. Okay, so just a little bit more about myself. Locally within Ottawa, I'm a member of two research groups, joint between Carleton and the University of Ottawa. The first is analysis, which very broadly speaking, you can think of as really a rigorous theory of approximation, if you'd like. And also this quasar group. So quasar stands for quantum, so QUA stands for quantum, S stands for security, A stands for algebra, and R stands for representation. So together it's quantum security through algebra and representation theory. So it's an interdisciplinary group of mathematicians, physicists, and computer scientists affiliated to the University of Ottawa in some way. And our website is you can find there. Okay, I'm also an affiliate member of the Institute for Quantum Computing in Waterloo, where I did my postdoctoral fellowship. So Angelo said a few things about my research. My research program lies at the confluence of several areas within pure mathematics and mathematical physics. But all these areas actually fall under one umbrella, and that is the mathematics of quantum theory. And one particular facet of my research program is in mathematical problems coming from quantum computing and quantum information, entanglement being a primary example. Okay, so let's recall that the fundamental unit of classical information is the binary digit or the bit, which can take one of two values, 0 or 1, right? And so we use the bit or very large numbers of bits to quantify the amount of information in a particular substance, for instance, or a particular object. Right, so for instance, you could think of a music file, which might be 5 megabytes, right? So a byte is really just a short form for 8 bits, and a megabyte means that you have 1,000,000 bytes, right? So it takes that many zeros and ones to encode all of the information contained in that music file into some storage device. Okay, so the bit is the fundamental unit on which we measure classical information. And physically, how can you model a bit? Well, any two-level physical system that can be in only one of two distinguishable states is a perfectly good model for a bit of information. So for instance, a regular toggle light switch, which can only be on and off, a two-sided coin, heads or tails, or the polarity of a magnet, for instance, north or south in directions. Okay, now the fundamental unit of quantum information is what's called the quantum bit, or qubit for short. Okay, now like its classical counterpart, a qubit can be either a 0 or a 1. Okay, now I'm going to use this the bracket notation around 0 and 1 to distinguish it from its classical counterpart. Okay, but nevertheless, a qubit can be in this 0 state or a 1 state. But unlike its classical counterpart, a qubit can also be in any superposition of 0 and 1. Okay, so mathematically, that just means some combination. So I'm not going to spend too much time on the mathematics here. But how you can think about this is that it's some kind of probabilistic mixture of 0 and 1. Okay, so these A's and B's that appear in this mathematical formula, they're numbers. And these numbers encode the probabilities that a measurement of this qubit state psi will yield either 0 or 1. Okay, so these qubits, they can be either 0 or 1, but they can also live somewhere in between, in a sense, which is mathematically modeled by this superposition. Okay, so my favorite analogy between a classical and a quantum bit is through light switches, which I find very helpful. So a classical bit is really just a light switch in a sense, or at least that's one example, right? A toggle light switch, it can either be on or off. Okay, well, if a classical bit is just a light switch of this form, then a qubit is really a dimmer switch. Okay, so with the dimmer switch, a usual dimmer switch, the light can be on at full strength, or it can be off, or you can adjust the brightness with some parameter, right? The dimming parameter, if you'd like. Okay, now, so really, if a classical bit is a toggle switch, a qubit is a dimmer switch. Okay, and now not only is it a dimmer switch, but it's actually sort of a two-dimensional dimmer switch in the sense that it has two toggles, A and B, which you can change independently of each other. Okay, so for instance, let's say you have a fancy light where you have a double dimmer switch. The parameter A, the A switch, it controls the brightness of the light that you see, and B could control the color of the light emitted, right? So you could independently change the brightness and the color simultaneously. Okay, so it's really a sort of two-dimensional dimmer switch in a sense. That's the analogy. Okay, so let's build on this analogy and let's come up with a picture which I find helpful, and it's actually somewhat physically accurate. Okay, so for us in this talk, a qubit is really going to be a spinning ball. Okay, it's going to be very microscopic, but just imagine some very, very tiny ball that's spinning. Okay, and to a body, a spinning ball in 3 dimensions, fixed in space, but spinning, you can associate a direction via what's known as the right-hand rule. So this picture of this spinning ball I have here on the slide, okay, the axis of rotation is the vertical axis of the slide, which is the direction in which this arrow is pointing. And it's spinning about that axis in a counterclockwise fashion. So what you do is you wrap your right hand in the direction of rotation, and whatever direction your thumb is pointing, that's the direction you associate to this spin. So this direction would be up because I curl my hand in the direction of rotation and my right thumb is pointing up. So this is spin up, if you'd like. And we think of this as the 0 state, the analog of the 0 state. Okay, so if that's the analog of the 0 state, then spin down is going to be the analog of the 1 state. Okay, and so here again, the axis of rotation is the vertical axis of the slide. Okay, but it's rotating about that axis in a clockwise fashion. So you take your right hand and you rotate you curl your hand around the direction of rotation, and your right thumb is pointing down. So you call that spin down. Okay, so all this is to say is that, you know, a fixed ball which is rotating in 3 dimensions, you can assign a unique direction associated to that via the right-hand rule. And we're going to think about qubits as those directions of spinning balls. Okay, and so the spin up state, which would be this spin configuration, that will play the role of the 0. The spin down state, which corresponds to this rotation configuration, will correspond to 1. Okay, but the qubit can be anything in between. And so if we play with these parameters, how you should interpret these parameters A and B, or their toggle switches in this rotation picture, is that you are rotating the axis of rotation defined by this line. Okay, so let's imagine A, by changing this switch on this A switch, what you're doing is you're just taking this first qubit in the 0 state and you're rotating this, this axis in a clockwise fashion, but it's going to stay on the plane defined by the page, or defined by the slide. Okay, so you're just rotating. And so as by changing that A dial, you're rotating that axis of rotation in this fashion. Okay, and by rotating the B dial, what you can do, this is a 3-dimensional rotation, so you can rotate it outside of the page, right? So you can rotate it, for instance, coming up. And so this arrow, if you will, imagine it's coming out of the page or out of the slide, pointing in your direction. Okay, so you can use these toggle switches A and B to really control the direction of the spin. Okay, and so viewing spin directions as really directions in 3-dimensional space, which are really, points on a sphere, if you'd like, any direction in 3-dimensional space can be thought of as, can be assigned a unique point on a sphere. And through that correspondence, think of A and B as just GPS coordinates, right? So A corresponds to, the spin state described by this superposition here, it corresponds to some spin direction somewhere. And that direction it's viewing that direction as a point on a sphere, it has GPS coordinates. It has a latitude and a longitude. So this A dial is really changing the latitude, albeit relative to the North Pole as opposed to the equator, and B is changing the longitude. Okay, so for us in this talk, qubits, and actually whenever you hear the word qubit, I suggest thinking about this picture if you're unfamiliar with qubits. So they're just really spinning balls, and the state of the qubit could be the ball, but spinning in any possible direction in 3 dimensions. Okay, so this sort of toy model that I presented here, it's actually somewhat physically accurate, and is related to this notion of spin. So all elementary particles in nature have an intrinsic form of angular momentum, which is known as spin. Okay, so different particles could have and this spin has 2 pieces of information, has a magnitude and a direction, spin direction as we just observed. Okay, so for different elementary particles, the magnitude of the spin could be different, which you can kind of compare to the rate of rotation, but the direction can change. Okay, so for instance, so a spin 1/2 particle, like an electron or a proton, this is an example of a qubit. So when I say spin 1/2 particle, what that means is that the magnitude, the fixed magnitude of the spin of the electron is 1/2 times a fundamental constant of nature, which is known as Planck's constant. Okay, so the electron, it has a fixed magnitude of spin, but it could be spinning in any direction. Okay, so this microscopic balls that we were talking about on the previous slide, these are really kind of electrons. And so, and the spin up state that we discussed, this is actually the spin up state of the electron, and the spin down state is actually the spin down state of the electron. So 0 is spin up, 1 is spin down. Okay, so this is a bit closer to reality than the dimmer switch analogy, but there's a bit of a caveat with this picture. I should mention that I've described electrons spinning, which suggests that they're spinning about their center of mass, just like the Earth, is spinning about its center of mass on a daily basis. So that's not actually happening for electrons. This spin, which is some form of angular momentum, it's not actually attributed to the electron spinning about its center of mass. So this picture is not entirely physically accurate, but at the same time, it's very helpful to keep in mind. So we're going to use this picture throughout. Okay, so for us, qubits are just really spinning balls. Okay, but they can be spinning in any direction in 3-dimensional space. And we're going to give names to the special directions. North, or the North Pole, spin up is 0, and the South Pole, spin down is 1. Okay, so that's the story for 1 qubit. What about 2 qubits? Okay, so 2 classical bits of information are really just given by bit strings of length 2, of which there are 4 possibilities, right? 0, 0, 0, 1, 1, 0, and 1, 1. So what are the quantum analogs of these sort of classical bit strings? Well, if we took two electrons that were both spinning up and we sort of put them together and you think of the combined system as one, then that would be, you have 2 particles which are both spinning up. So we call that 0, 0. And similarly, if you have an electron which is spinning up and you have an electron which is spinning down, and you sort of consider them as a whole, and then you can denote this state by 0, 1, okay? And similarly, if the first particle is spinning down, the second particle is spinning up, this would be the state 1, 0. And if finally, if both particles are spinning down, then we call this the state 1, 1. Okay, so these are the quantum analogs of these classical bit strings. But of course, that's not the entire picture. Just like in the case of single qubits, they weren't just 0 or 1, they were any superposition in between. And so any 2-qubit state, an arbitrary, a more general 2-qubit state, could be any superposition of these 4 states. In particular, let's say this one. Okay, so we take, okay, don't worry about this constant here. We take some mixture of the 0, 1 and 1, 0 state, which is spin up, spin down, and spin down, spin up. Okay, so in pictures, we can define this state here. So it's some mixture of some combination of the state where the first particle is spinning up, the second's down, and the state where the first particle is spinning down and the second one spinning up. Okay, so this state, this is a valid state according to the laws of quantum mechanics. Unfortunately, unlike the single qubit case, we kind of lose that sort of rotational interpretation of the coefficients in this superposition, but nevertheless, this is a valid state. It's an important state. It's often called the singlet state, and we will refer to it as such throughout the talk. Okay, so this state has a peculiar feature. You cannot write it as a concatenation of 2 independent qubits, regardless of how they may be spinning. So in pictures, there do not exist single qubits, let's say psi1 and psi2, which could be spinning in any orientation, so that if you concatenate them together in this way, that gives you the state psi. It's not possible. Okay, so you can prove that. It's actually not that hard. So in words, what I'm saying here is that this singlet state psi, it cannot be separated, if you'd like, into a product or a concatenation of 2 independent qubits. It's just not possible. They give you a different state. Okay, and this is actually the definition of entanglement in the context of 2 qubits. Entanglement means that you cannot sort of factor the state, you cannot describe the state by giving independent descriptions of its constituent particles. Okay, so unlike our sort of bit string states that we had on the previous slide, right, these states were described exactly by the properties of their individual constituents, right? So it's a 2-particle state. We know that both particles are spinning up. We call that 0, 0, right? So all these 2-bit states that I described, these are not entangled precisely because they are these so-called product states. They are described by the independent properties of their constituent particles. Okay, so the fundamental feature of entanglement is that they do not admit descriptions by the properties of the constituent particles. In other words, the whole is greater than the sum of its parts. That really summarizes entanglement in a nutshell. Okay, so mathematically, we can't sort of separate entangled particles into products of 2 independent ones, and physically, actually, entangled states you can't separate them from the perspective of measurements either. So although this singlet state psi, it physically is comprised of 2 spin 1/2 particles. It's a state of 2 spin 1/2 particles. There are 2 particles out there, but it actually behaves like a single entity with respect to spin measurements. So for instance, if let's say, Alice, you have 2 parties, Alice and Bob. Alice has access to the first particle, Bob has access to the second one. And they want to determine the spins of their individual particles. And so they make a measurement of spin. So the probability so 0, 0 here encodes the outcome that they both are spin up. So the probability of both Alice and Bob measuring spin up is 0 because the up state appears nowhere in the description of psi above, essentially. Now the probability of Alice measuring spin up and Bob measuring spin down, well, this is actually 1/2, and that's a consequence of the fact that sort of state of up down appears in the description of psi. Okay, and okay, there's a bit of a change here. I went from square root to square. Don't worry about that. That's just because the probability is a quadratic function of the state. Anyways. Okay, but similarly, the probability that Alice will measure spin down and Bob measures spin up, this is also 1/2 for the exact same reason. Okay, and the probability that they both measure spin down is 0 again because that state is not in the description of psi itself. Okay, so the possible outcome, there's only 2 actually possible outcomes of this experiment because these 2 outcomes have probability 0, they'll never happen. And you have these 2 outcomes here. Either Alice is spinning up and Bob spinning down, or Alice is spinning down and Bob is spinning up. And there's equal probability for these outcomes. Okay, so really we have perfect correlation between, or anti-correlation, more specifically, between the spins of Alice's state and Bob's. Right? If Alice sees a 0, which means spin up, then Bob's is necessarily 1 or down, and vice versa. Okay. All right. So we have perfect correlation. Okay, great. But you can make the argument that, okay, in life, there are even macroscopic, random variables that are perfectly correlated. For instance, the time that I wake up in the morning and the time that my son wakes up in the morning is perfectly correlated, right? So what's the big deal about entanglement? All right, well, let's think about this example a bit further through the lens of the people who first brought this to light, which was Einstein, Podolsky, and Rosen in their seminal paper in 1935. So the example that I'm presenting here of this singlet state, it wasn't quite exactly what they presented. I'm presenting a simplified version, which was given by David Bohm several years later, but the ideas are identical. Okay, so Bohm considered the decay of a spin 0 particle. So for us, that's this circle in the middle here. It's going to decay through some process into 2 spin 1/2 particles. Okay, and there are examples of this that you could actually write down, physically meaningful examples or instances of this. Now, because you started with a spin 0 particle and you obtained 2 spin 1/2 particles that are actually spinning, have non-zero magnitude of spin, well, by conservation of spin angular momentum, the particles have to be spinning in opposite directions, right? If you started with something which has 0 spin and you produce things which have spin, well, their spins have to cancel in order to conserve angular momentum. Okay, so one of these particles is spin up. Okay, for simplicity, let's assume that the axis of rotation is aligned with the slides. Okay, so under that assumption, one of the particles is spinning up and one of them is down, but we don't know which one is which. Is the left one spinning up or is it spinning down? We have no idea. And so the appropriate quantum mechanical description of the joint state of these 2 spin 1/2 particles is our friend, the singlet state. Okay, now, just as we did before, let's suppose that the left particle is sent to Alice. And let's suppose that Alice is is in a very nice lab on Earth where she can make spin measurements. And let's suppose that the right particle is sent to Bob, who's actually in an equivalent lab, but on Mars, hypothetically. Okay, and Alice measures the spin of her particle. Okay, now by the perfect anti-correlation of these spin measurements, as we saw, if she measures spin up, the outcome of her measurement is spin up, then Bob's particle must be spinning down, right? They have to be opposite by conservation of momentum. Right? And if she measures spin down, then Bob's particle must be spin up. Okay, so effectively what's happening here is by Alice making a local measurement on Earth, she's actually learning something about the state of a particle which is on Mars. And she learns this information more or less instantaneously. Okay, moreover, according to the standard interpretation of quantum mechanics and standard, okay, this is, by that I mean that of Niels Bohr and Werner Heisenberg, This is also sometimes called the Copenhagen interpretation. And it's really the one that is taught in most undergraduate and even graduate level quantum mechanics courses. So the interpretation is that the direction of a particle's spin is actually an indeterministic quantity of nature. It's not a well-defined property or element of reality, but rather it's an attribute of the interaction with a particular observable. Okay, so by that I mean it's not that Alice's particle is spinning in a certain direction, and the observation just reveals the direction in which it's spinning. The interpretation is that actually the direction of spin is not even well defined. It doesn't exist until you have this interaction. So it's actually a consequence or an attribute of the interaction given by the measurement. Okay, so according to this interpretation, which is really kind of the standard go-to interpretation of quantum mechanics, there are others, but according to this interpretation, Bob's spin state is actually results from Alice's local measurement. Okay, the spins are unknown, but Alice makes a local measurement on Earth, and she realizes, okay, hers is 0, and that arises as a consequence of the interaction there. But if hers is 0, then by conservation and momentum, Bob's has to be 1. So effectively, what she's done is she's actually, the fact that Bob's is spinning down is a consequence of the local interaction between Alice's half of the entangled pair and Alice's measurement, which is crazy. How is this possible, right? So Einstein was a realist. He thinks that, he thought that objects ought to have well-defined properties like spin directions, position, energy, momentum, right? It's not, they're always there, and observation just reveals their value to you, right? He's often quoted by saying something to the effect that, just because you're not looking at the moon doesn't mean that it's not there. Right, and so EPR, they argued that this example of the singlet state proves that quantum mechanics is an incomplete theory. There's something baffling here. Something's wrong. Okay, but it turns out that through interesting work of John Bell and its subsequent experimental verification, this EPR argument that they made in their paper was shown to be false in the sense that at least one of their assumptions is incorrect. Okay, now precisely which assumption and the ensuing interpretations are debated to this day. I'm not going to go into the details. You could fill good portions of large libraries with literature on this subject. It's vast, it's interesting, it's deep, but it's very complicated. In any case, we're not going to go there. Whatever the answer to this paradox might be, entanglement, as defined by this inseparability and as exemplified by the singlet state, is viewed as a form of non-local correlation. So what the difference is here is that, yes, you have these perfectly correlated observations, but this correlation somehow transcends space to a certain extent. It's non-local. You can have this correlation in theory between someone on Earth and someone on Mars. And by locally making an action on Earth, you can actually have an effect on something on Mars, seemingly instantaneous. Okay, so this seems like a very, very powerful tool if we can exploit this, and that's exactly what's done in quantum information. Entanglement is actually the fundamental resource for quantum computing. Okay, and there are a variety of applications. So I'm going to mention one that I find particularly fascinating, and that's teleportation. Now, when I say the word teleportation, of course, you're probably thinking of Star Trek, right? And you stand in the right place at the right time, and all of the matter and energy that makes up your body is going to be taken from someplace and reappear in the exact same configuration somewhere else in the universe. That's not what's happening at all. Okay, so, but what is happening is actually more accurately described by this picture here. Okay, which I will attempt to explain. So this protocol was introduced in the early 90s, and the idea is that they want to teleport the state of a single qubit. It could be an arbitrary state. So this qubit is, again, qubits are little balls rotating. It could be rotating in any direction. But the point is that Alice wants to send that state to Bob. So the qubit, this qubit inputted to Alice, it better be the same as what Bob outputs after this, okay? And so how do they do this? So there's this EPR source here, which produces this entangled pair. For example, our friend, the singlet state. Okay, one half is sent to Alice, one half is sent to Bob. So Alice has access to one half of this entangled state, but she also has access to this incoming state to be teleported to Bob. And how does she do this? Well, Alice makes a particular measurement. I'm not going to go into the details. It has 4 outcomes. And depending on the result of that measurement, let's say outcome 3 happens, she's going to communicate that result to Bob through some classical mean. And the outcomes of this measurement, I should say, are just numbers. I mean, they're bit strings, 00, 01, 10, or 11. She communicates that bit string corresponding to the result of that measurement to Bob through some means of classical communication, which could be a text message or a phone call. Okay, then Bob has a list of operations parameterized by the outcomes of Alice's experiment. And if Alice measured, if the result was 10, she tells Bob, he's going to say, I'm going to pick my 10 operation, apply it to my half of the entangled pair. And magically, that half is going to be transformed into precisely that qubit state that you started with. Which is crazy. So essentially what's happening here is through local operations and classical communication. So Alice makes a measurement locally on her side. She communicates the result of that measurement to Bob through some classical means, and Bob does a local operation on his side. Why? Okay, so assuming they have this entangled resource to start with, that's of course very important. Then by just performing local operations and classical communication, they can effectively teleport quantum information. They can send quantum information from one place to another. Okay, so this is an extremely useful protocol, and it's used all the time in quantum information. In one very interesting place that it's used, that it was used to develop a theory of fault-tolerant quantum computing. And other instances of entanglement, as I mentioned, it's used everywhere in quantum computing. It really is kind of the resource which distinguishes quantum computing from classical computing. It's used in fundamental quantum algorithms, in particular, Shor's famous algorithm. You may be familiar with Shor's factoring algorithm to factor large integers. And it's also used to establish security of quantum encryption schemes in quantum cryptography. Okay, so I'm running out of time here. Just one last thing I'd like to mention concerns some current research directions, which I find particularly interesting. And this falls under the purview of this IT from Qubit program, which is a Simon's collaboration on quantum fields, gravity, and information. So the idea here, so recent results have shown that ideas from quantum information shed valuable insight into open problems in quantum field theory and quantum gravity, and vice versa. So ideas from these perhaps a priori disparate fields can actually be used to gain some deep insight into problems in respective areas. So this motivated the Simons Foundation to fund this international collaboration. And the principal investigators are distributed around the world. So you have people from Stanford, MIT, Princeton, Caltech, Kyoto, University College London, and the Hebrew University in Jerusalem, for instance, and even more that are collaborating on this. You have principal investigators locally here in Canada and at the Perimeter Institute, McGill University in Montreal, and the University of British Columbia. Okay, and they're studying many questions surrounding the connection between quantum information and quantum gravity. But one question which I find very fascinating is that, does space-time itself emerge from entanglement? So it's been shown that at least in some models of space-time, which, okay, are not directly applicable to our universe as we know it just yet, but nevertheless, in some models of space-time, it's been shown that geometric properties of space, or really gravity, which is manifested in some geometric property of space, is actually encoded or some manifestation of some underlying entanglement structure. And so that led to this question, does space-time itself actually emerge from some underlying entanglement structure, which sounds like science fiction. But honestly, there's an entire industry of mathematicians and physicists and computer scientists who are studying this and related questions. And it's bound to produce some fascinating results. Okay, so I just wanted to list some further information that I can elaborate on in the question period if you're interested, but thank you for your attention.
Okay, thank you very much, Jason, for a very visual description of entanglement. It's wonderful. So we have a question here from Catherine. And the question is, can you explain quantum teleportation again? Got lost among the zeros and ones. What exactly does Alice communicate to Bob?
Right. Perhaps I will share my screen again. Maybe I should just remain shared. So, sorry. Okay. Right. So the measurement that Alice makes here, this is abbreviated by BSM, which stands for Bell state measurement. So there's a family of 4 states of 2 qubits known as the Bell states, and the singlet state happens to be one of them. And the measurement that she makes, and so there's 4 of them, and so they can be indexed by a two length bit string, right? So 0, 0, 0, 1, 1, 0, or 1, 1. And so the measurement has 4 possible outcomes, parameterized by 2 bits of classical information. And so she measures, so this is a joint measurement on 2 qubits. So this is sort of a 2 qubit measurement. And she's making that measurement on this particle 1, which is the one to be teleported, and her half of the entangled pair that she shares with Bob. So she's making this measurement on those 2 particles. And somehow the act of that measurement, through the entanglement that exists between Alice and Bob, the act of that measurement, somehow it transforms Bob's, basically it transforms Bob's state into one of 4 possibilities, parameterized by 0, 0, 0, 1, 1, 0, or 1, 1. And Bob can basically, so those states aren't quite those are going to be single qubit states, but they're not quite the ones she wants to teleport, but there's some transformation of that state, again, parameterized by these bit strings. So to get the state to be teleported, Bob has to undo that sort of action, which was sort of inferred from the local measurement on Alice's side. And in order to, he doesn't know which one. Okay, it's one of them. There's one of 4 possibilities of equal probability. But as soon as he learns the outcome of that measurement, that's why we need this classical communication. He can undo that measurement, because he can undo that operation, sorry, to recover the original state of interest. Right. So I don't know if that answered your question. Hopefully.
So let's move on to the next one. The next one is by Michael. And this question is, how does one use entangled particles to communicate without the classic information limitation?
Right, that's a good question. So yeah, if you don't, so basically, how do you, if you don't have classical information? Yeah, I mean, classical information is crucial to this teleportation protocol, right? And you couldn't do it. I mean, Bob could guess. I mean, you could just play a guessing game, right, and make it a probabilistic thing. You say, I don't know what the result was, but I mean, I can make a guess. I mean, it's not very useful. He'll be correct a quarter of the time, all right. But that's obviously not very systematic. So perhaps let me just say that. So this, I mean, people study this kind of question, and then so there are many that question leads to a number of other questions. So essentially, what your question falls under the purview of the following. So you have, let's say you have 2 parties, Alice and Bob. You want to communicate some quantum information or send qubits one to the other through some means, through some channel. Okay, and so this. You can sort of put the classical information and the entangled resource together into a mathematical operation, which goes from Alice to Bob. And that mathematical operation will have a particular structure based on this resource state and the classical communication. So we call this operation an LOCC operation, because it's local operations and classical communication. So if you remove the classical communication, then you remove the CC part in that, and now you're just looking at local operations. And so there are some partial, I mean, there are some results in the literature about this. But there are, of course, some limitations on what you can do, depending on what you want to do given the certain setup. Okay, so sorry, it's not really a good answer to your question, but I'll just say that question and similar types of questions are studied in quantum information. But I don't have like a specific. I mean, it depends on what you want to say, what you want to ask. Like one. So if you shared entanglement, I mean, yeah. So okay. So if you only had access to shared entanglement and you didn't have classical communication, then this operation, if you view this mathematically as an operation from Alice to Bob, this operation, we call it a quantum channel. It's a certain type of quantum channel, and given a type of quantum channel, an information theoretic quantity of interest is this so-called capacity, which measures basically the amount of information that you can send between Alice and Bob. Okay, and for a particular channel, actually, computing this capacity explicitly can be really difficult, even for simple examples, and even coming up with non-trivial estimates on how much information you can send and at which rate is really non-trivial. And so this really, I mean, this falls under the purview of quantum information theory, and there's an entire sea of literature devoted to studying the capacities of different types of quantum channels. So like I said, it would depend. So really, for that kind of question, you have to sort of pin down the channel you're working with, and the domain and range. What does Alice have? What does Bob have? And in order to be able to understand that, or to study that question, but you would do it under this guise of quantum channel theory. Yeah.
Okay, we can move on, I think. There's a comment from Anne here, and the comment is the following: your point about entanglement and space-time also made me think of fractals. Probably irrelevant, but I wonder what role, if any, that could play.
Right. Yeah. So I guess I had a fractal type picture on that slide. Right. So yes. So in some of these toy models, where these fractal images come from is these are kind of discretizations of space. So here in this particular instance, space is a circle, it's a disk, and the boundary is the boundary circle. And how one way to discretize that space is to tessellate it with certain tessellations. So just like imagine you could if you look at the screen, you could tessellate the screen with a bunch of squares, right? You can have this rectangular grid and you have a bunch of squares. That would be a tessellation. So here, the idea is the same. It's a bit more complicated because the geometry there is so-called hyperbolic, and so that the kind of the squares that they're using, they're not actually, they're kind of hyperbolic squares in a sense. But the idea is that, and these tessellations often have sort of fractal type structure, and in particular, kind of what's happening near the boundary is very sort of fractal in nature. So I would say that these kind of fractal designs come up quite a bit in toy models, and I mean, it's not clear exactly, I mean, to what extent the self-similarity, which is the fractal type nature of these discretizations, comes into play. However, it should be there in some places. And I know one example where it's used to calculate some quantities of interest. So there's at least one example where the fractal nature does come up. I'm not sure how fundamental it is at this stage, but seeing that it is used to, I mean, these fractals kind of come up all the time as discretizations. I would imagine that the fractal nature should play an important role.
Okay, let's move on. Next is a comment by Richard. Is the range of possible superpositions between spin up and spin down quantized, or are all intermediate mixed states possible?
By a mixed state, I mean, one can interpret that in two ways. So there is a notion of a mixed state, but that's not what we're referring to. But yeah, I mean, in principle, yes, any spin direction is possible. And I mean, I've restricted the discussion to measurements of spin relative to the vertical axis of the slide, right? But really more precisely, what you should do is you can, given any direction in space, there's an associated spin measurement, and that would measure, to what degree that particle is spinning in that direction. So in principle, all possible directions are achievable. Yeah, and are used, in fact, in practice.
Another comment by Michael is that quantum teleportation seems more like just a way to do encryption. Do you want to comment on that?
Yeah, I mean, it's a way of sending information in a way. Yeah, exactly. So it's because you're kind of sending quantum information. I mean, kind of a natural model of an eavesdropper on this process would have no information, because the eavesdropper would typically has access to the channel that Alice and Bob are using to communicate, in which in this case it's classical, right? So if someone who's eavesdropping on this measurement, that what they can intercept, the text message that was sent from Alice to Bob, but all that eavesdropper would get is some bit string like 10, and they would learn nothing about the actual state to be teleported. So exactly, I mean, this you can interpret it in that fashion.
Okay, and question by Saman. Are the parameters A and B interrelated by normalization of the composite wave function?
Exactly. So there's relationship I didn't write down, but so these A and B's are actually complex numbers, but a complex number has a modulus, which is some kind of like absolute value, and the sum of the squareds of the moduli of A and B have to be 1. So this comes from the normalized. I mean, you always think of these wave functions as being normalized, and that normalization has to do with the probabilistic interpretation. And so yes, so that's always in the background.
Okay, and we have another one. There's a number of questions, so I'm trying to go chronologically here as opposed to the order that I get them on the Q&A. Got the water? Okay.
Sorry.
How does Bob keep his half of the entangled pair suspended until he receives the classical information from Alice?
Right. So that's a good question. Well, in a sense, the entanglement is destroyed as soon as Alice makes her measurement. So 2 comments. So the first is as soon as Alice makes her measurement, that actually destroys the entanglement between them. It's destroyed. But what comes out at the end is some signature of the initial state to be teleported. Yeah, so when Alice makes her measurement, the entanglement is destroyed. It's no longer there. But somehow through properties of this measurement, you can think of kind of the information of this qubit to be teleported. It sort of travels through the measurement and then through the entanglement, and then the entanglement kind of gets sucked up, and it sort of ends up as a transformation on Bob's half. So it's somehow used up. So that's what's happening. But now your question also points to another one, which you may be referring to. I mean, in practice, to maintain the perfect entanglement that you need to get this, to teleport this perfectly, can be extremely difficult, right? And often there's some experimental difficulties, and what you get in the end is not exactly the original qubit, but something very close. And so maintaining the entanglement until Alice can do this measurement is also, I mean, there's some engineering complications which come in there. But people have been able to do this, over hundreds of kilometers, and even in 2017, some scientists in China were able to actually maintain entanglement between a ground level observatory and a satellite at a distance of a maximal distance of 1,400 kilometers. So, I mean, the entanglement wasn't perfect, but it was large enough for them to actually to achieve this protocol. I mean, not perfectly, up to some percentage of error, but anyways, I think that's all I'll say.
Okay, thanks. Now, I don't have any further comments or questions, but if you do, please type them into the Q&A or into the chat box. We still have a few minutes.
So maybe while we wait for questions, I mean, you can stop me, Angelo, if,
Sure.
did one come up?
No, not yet. We still have about 9 minutes.
But I feel like the QA numbers increased. I don't know if,
Oh,
okay.
wait a minute. No, thank you. You get a lot of thanks. So.
Oh, I see. All
Yeah.
right. So yeah, so I'll just maybe mention, I mean, if you're interested in learning more about qubits and quantum computing, entanglement, and this, connection with space-time, I thought I'd mention a few additional resources. So this Quantum Tamers, this was a documentary that was made out of the Perimeter Institute and Institute for Quantum Computing. It's a very, I mean, this was done, I think, in like over 10 years ago, but so certainly, I mean, quantum technology has been updated since then, but I find this to be a very insightful description of quantum computing and the goals, some of the large scale goals of quantum information more generally. Also, there was an address that was given by John Preskill about 4 or 5 years ago at a Quantum Computing for Business conference, I believe. It's called Quantum Computing in the NISQ Era and Beyond. So NISQ stands for Noisy Intermediate Scale Quantum Technology. So this is a very well written document. It's a paper. It's written for the general public. It's not written for the specialists. There's no mathematical equations. And John, who is really a leader in quantum information, it really explains his view on where quantum technology stands, especially from the perspective of business. So if you're interested in that, I highly recommend reading this article. Also, there's a fairly new consortium of Canadian quantum technology companies known as Quantum Industry Canada. So if you just Google that, you'll see there's a growing list of startup companies who are all working on developing various quantum devices for applications in industry and other areas of science. In one article, which I find particularly accessible, written by George Musser, he's a contributing editor for the Scientific American magazine, and it's entitled "What is Spacetime?" and really he's giving sort of an overview, a more detailed sort of picture of this connection between, or potential connection between, entanglement and spacetime. And so you can find that here if you're interested.
Okay, well, thanks a lot. I think we can probably end early. And in the meantime, I can say that you can always get a hold of this talk. It's being recorded to the Faculty of Science's website. And thanks again, Jason, for this excellent talk on quantum teleportation and wonderful. It was just great. Yeah, thank you so much. And thank you all for participating today.
Thank you.
We'll see you at the next Science Cafe. Right, bye-bye.